For this lesson and our new unit, we're going to be looking at curve sketching, and in particular we're going to be taking a look at the idea of increasing and decreasing functions. Now we're going to want to look at these in the context of calculus, but this concept is something that should already be familiar to us from our advanced functions course. So here I've given you what appears to be, and I can tell you what actually is. This looks like a cubic function. And I'm asking on what intervals is the function increasing and on what intervals is the function decreasing. So if we first of all just think about where is it increasing, whenever we talk about, first of all, whenever we talk about these labels of increasing or decreasing, the thing I want you to remember is that we're always talking about from left to right. Okay, and that means actually I'm going to say my x value from left to right. So that means when I talk about something increasing or decreasing, what you have to imagine is that you have some invisible line, which I'm going to use this vertical line to represent, and you are moving this invisible line from left to right, and you're watching to see how is the curve behaving as I move that line. And you're going to span the entire visible function with that line. So it's almost like you're scanning it, but you're always going to be scanning it from left to right. And so if I repeat that with that in mind, let's just take that first look at it with that definition. So I have to move it to here. Okay, so now it's actually touching the function. And so where it's touching the function is going to tell me what's happening. As you can see there, as I move my dotted line here, as I move my vertical line, the place where it touches the function is moving up and up and up. So it is actually increasing right now. And then I get to this point, which is a peak on the function, which from calculus we have learned to describe as a local extrema, or in this case this is a local maximum. And now what happens at that local extrema as I continue to scan from left to right? Notice what's happening to where my graph intersects this vertical line. Now that point of intersection is moving down. And it continues to move down, it continues to move down until I get to this point, which is a local minimum. And then we continue our scan from left to right, and you can see that it starts to go up again. So with that idea, what we have happening, first of all, we had that the function was along from here. Let's see, let me grab another color. So as it was going from here to here to here, we can see the function is increasing. When it reaches this point, we have a local maximum. I will switch colors now. Then, as we slide along from here to here to here, we have our function decreasing. And then when it gets to this point, which I'll emphasize with a slightly larger point, we have a local minimum. Hold on a second. Let's try to spell that in a civilized way. Local minimum. And then from this point forward, we are once again increasing, because notice that as I did this, I went from left to right the whole time. So in what I did there, I was looking at this just from a very common sense point of view, the idea of increasing, the idea of left to right. Now, is there another way that we could look at this? And it's a bit of a loaded question. The answer is, of course, there is. And in order to do that, what I'm going to do is I'm actually going to go back. So let's go back to what we were talking about with regards to a local maximum and a local minimum. Now, I know those are definitions that we talk about more in calculus, And how do we get to those definitions in calculus? We get to them by looking at the slope. So in both of those cases, at this local maximum, we had a slope of 0. And at this local minimum, we had a slope of 0. So if that's the case, if the presence or the location of a local maximum or a local minimum or any local extrema has something to do with a slope of 0, then how can we define the idea of increasing or decreasing in terms of slope? And the way that we do that, if we take a look, I'm just going to pick any point along where I said it was increasing. That's not what I meant to do. Hold on a second. I wanted to use a straight line. And let's just put that there. And what can you tell me about the slope along that line? Here, where we said it was increasing, my slope is positive. Similarly, if I were to draw a straight line along here, quite obviously, we have a slope of a negative value. I used the word obvious there. I apologize. Pet peeve among some of my students. And over here, I put in a straight line, and the slope is, once again, we are increasing. The slope is positive. And you know what? It is obvious. If you can't tell that you have positive slopes here and negative slopes here and positive slopes here again, then you really need to question whether or not you know enough about graphs when it comes to a course like calculus and vectors. So that being the case, this idea of the function increasing or decreasing or increasing is tied to slope. Positive slopes and negative slopes for increasing and decreasing. When the slope is 0, the function is neither increasing nor decreasing. It means it has reached an extrema, either a maximum or a minimum, usually a local max or a local min, as it is in this case, but it could also be an absolute maximum or minimum. Another way to see that visually, I've done it here with color. So over here in this blue box, all of the tangent lines in this interval have positive slopes. Here, where it is decreasing, all of the tangent lines in this interval have negative slopes. And then once again, we pass that local extrema where the slope is 0, and once again, we're looking at only positive slopes. So we're going to want to attack this idea of intervals of increase and decrease not quite in the same way that we looked at it in advanced functions. We're going to look at it from a calculus perspective, and then in the lessons going forward, we're going to take that further and expand upon it. So in this case, let's take a look at this one. Let's look at this purely from a calculus perspective. Now we know that something special occurs when the slope is equal to 0. Those are known as extrema. And I can see that I have a slope of 0 here, and I can see that I have a slope of 0 here. So let me mark those points. So there I have a slope of 0, and here I have a slope of 0. And now I ask myself, well, what's happening over here? And if I put in just a couple of lines, and I try to draw tangent lines, even though they're shallow, you can see that those tangent lines are negative. So here we have a slope that is less than 0, and that means that this function is decreasing. And then along here, my tangent line, I'm just going to go ahead and put the one through the middle here to represent a positive slope. So now my slope is greater than 0, which means it is increasing. And then finally over here, I once again have negative slopes. which means I am decreasing. And so when I answer this question, and I actually identify the intervals on which the function is increasing, now I'm going to have to do a bit of an estimation here, but I'm going to eyeball this, and it looks like this is occurring at -1, and this is occurring at +1. So the interval of increase was between this local, actually in this case it's an absolute minimum and maximum, but they're also locals. So between this slope of 0 and this slope of 0. And so that is between -1 and +1. And since when the slope is 0, it is neither increasing nor decreasing, this is an open interval as opposed to a closed interval where we would use square brackets. That means it does not include -1 and +1. So there is my interval for increase. My interval for decrease is going to be from -infinity to -1, but it's not going to include, obviously we cannot include -infinity, and we shouldn't include -1, and it is the union with +1 to +infinity. So that would be my interval where the function is decreasing. So using a derivative, we can come up with some meaningful statements about intervals of increase and decrease, and we can come up with those things algebraically. So the way we do it is for any function f of x, we take the derivative, f prime of x, and if that derivative is positive, then we have identified an interval of increase between a and b. If that derivative is negative, we've identified an interval of decrease. Now the thing we're going to use to identify these intervals is actually going to be the key we're going to be checking here. I'll put it this, actually I'll do it in a third color, is we are going to be testing where f prime of x equals 0. And by testing where f prime of x is equal to 0, we can then check and see where is it positive and where is it negative. And I'm going to do an example to show you that. Now, in order for us to be able to do this, we have to be dealing with a function that's continuous and differentiable. In general, this is going to be the case, but you do need to be aware of it. Now, we haven't talked very much about functions being differentiable because everything that we've been dealing with actually has been differentiable on the values you've been asked about. And it's actually a fairly simple definition. A function is differentiable if at any value a, you can actually substitute the value a into the derivative. So that means it's differentiable. Quick example, I'm trying to think of something. For example, well, if f of x is equal to 1 over x, then f prime of x is equal to -1 over x squared. Well, in this case, neither the function, the original function itself, nor the derivative, we can't use a value of 0, for example. So this function is not differentiable at x equals 0, or at the value x equals 0. That's just a very crude, simple example. You may come across, you probably will come across other examples. So it is something you have to keep an eye open for. Okay, so find the intervals of increase and decrease for this polynomial. And so the first thing we're going to do is we're going to take the derivative. So we end up with f prime of x is equal to, and this one's quite straightforward. We're just going to be using the power law on this one. So we end up with 12x cubed plus 12x squared minus 24x for the derivative. Now, the next thing we're going to need to do here is we are going to set f prime of x equal to 0. And remember, why do we set f prime of x equal to 0? It's because we are looking for the local extrema. And you always do need to include this part at the very least. It's never a bad idea to include actually a little note about why you're doing it, to show me or to include in your solution that you understand why you're doing this. So we get 0 equals, and I'm just going to go ahead and start factoring this right away. So I immediately see a common factor of 12 and also a common factor of x. And that leaves me with an x squared plus x minus 2 inside the bracket. And I can continue to factor that. I have a simple trinomial here. And so two numbers that multiply to negative 2 and add to positive 1 are going to be x plus 2 and x minus 1. So that actually factored quite simply. That's about the best you could hope for here. So this is obviously an example that's on the simpler side. And so what are my possible solutions here? Well, 12 can't make this thing equal to 0, but x can. So we end up with x equals 0, or x equal negative 2, or x equal positive 1. So those are my possible solutions. Now, I have found out where the local extrema are, but remember, the question's asking me for intervals of increase and decrease, which means I'm interested in when is this f prime of x greater than 0 or less than 0. And when it comes to testing for greater than 0 or less than 0, an interval table is well suited to something like that. So what I do is I take the values that I found and I put them in order, so negative 2 and then 0 and 1. And I need one extra line here because I'm going to put my factors down the side here. You could put 12x here, or you could just put x. You just have to be careful in case this is a negative value. Make sure you preserve that. So I'm going to go ahead and put 12x, and then I'm going to put x plus 2, and then I'm going to put x minus 1, and then I'm going to put my result. Or actually, you know what? Let's put what it actually is, which is f prime of x. So we pick a number that is less than negative 2, but that is on the domain of this. Now, since this is a polynomial, for a polynomial, the domain of that is just x member of the reals. And for every polynomial, its derivative is simply a polynomial, which means that its domain is also everywhere. And that also means it's differentiable everywhere. All polynomials are differentiable everywhere. They're continuous everywhere. So if I choose a negative value here, if you want to, you could put in an actual negative value and substitute that in. And so in this case, for example, you would get negative 36. But we don't actually care about the 36 part. We just care about whether it's positive or negative. So I just want to pick a value that's to the left of negative 2, and I realize that I get a negative there, I get a negative there. When I multiply those three negatives together, I actually end up with a negative. Then here, between negative 2 and 0, again, if I wanted to, I could put in a value, but all I really care about is the fact that this one is a negative, this one is a positive, and this one is a negative. And so that ends up being positive. And then between 0 and 1, now things get a little bit awkward. Sure, you could put in 0.5, but the important thing is you just want to recognize that this is going to be positive, this is going to be positive, and this is a small number for x, so a small number minus 1 turns out to be a negative. So this is a negative. And then here, again, a big positive number, or you could just put in 2, and we end up with positive, positive, positive. And so overall, that ends up being positive. Now, unlike when we use the interval table in advanced functions, we were usually solving an inequality, which would cause us to decide whether or not something was rejected or whether it was a pass or a reject. But here we're trying to identify intervals of increase and decrease. So here the slope is negative, so that means it is decrease. Here the slope is negative, that means it is decrease. Here the slope is positive. Remember, slope is the first derivative, so that's an increase. Here the slope is positive, that's an increase. So now my solution is my intervals of increase, which we quite often will just say increase. That's going to be x member of, and then we just define our intervals of increase. That's going to be -2 to 0, union 1 to infinity. My intervals of decrease, now you could also use set notation for this. So let me just go ahead and switch notations. This is x member of R such that, how am I going to say this interval of decrease? This part is going to be x less than -2, comma, and then the other part of this is going to be 0 less than x less than 1. Set notation or interval notation, I would say I have a preference for interval notation, but that doesn't mean I'm going to penalize anyone for that preference. I just actually think that this is a nicer notation for what we're doing here. But both of these are correct and acceptable. So if it's not specified, you choose which one you like. Given the graph of f prime of x, so that's what this blue line is. This is the graph of f prime of x. Find the intervals of increase and decrease of f of x. So that's saying, so what does it mean to be intervals of increase? So that's worth pointing out. Increase means that the slope is positive. So let me actually put that in. Increase means the slope is positive, and in particular, let's go a little further than that. It means the slope of the tangent is positive, but that's the same thing as saying that f prime of x is positive. Decrease means that f prime of x is negative. So now let's look and see, well, where do we have f prime of x being positive? F prime of x is positive everywhere to the right of -2. So my interval of increase, if I move this down a bit, I can actually write in my interval now. My interval of increase is x member of, and it starts at -2, and it looks like this if we assume that this has arrows on the end. That goes to infinity. My interval of decrease is x member of, and it's going to be everything to the left of -2. So that's -infinity to -2. So there's my answer to part A right there. Find the x values of the local extrema. Now we've answered that already, really, because we used that x value of the local extrema as our cue for knowing where to split our intervals of increase and decrease. So the answer to B is the local extrema, and again, let me just add a little notation here to explain where this is coming from. Local extrema come from f prime of x equal to 0. And so where is f prime of x equal to 0? That is occurring at x equal -2. So that is my local extrema. Or at least that is the x value, or the x coordinate of the local extrema. And now let's sketch f of x, assuming that f of 0 is equal to 1. Now I had to give you that f of 0 equal to 1 so we would have some sort of starting point for this. So for this I'm going to do this in red. So I'm going to show f of x in the color red. I know that f of 0 is equal to 1, so I know there's a point here. Now, from -2 to infinity, so everything to the right of -2, so let me go ahead. I'm going to put a vertical line here through -2 because that's very important. Everything to the right of -2 is increasing. From -2 to infinity, we are increasing. So that means going through this point, everything has to be going up and up and up. Everything to the left of -2 is decreasing, but we have to remember our definition of decreasing, which means we start at the left and then we move to the right. So that means it has to be coming down, 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 down until it gets to here, and then it has to be going up again. So that means we have to have a local and an absolute minimum somewhere along here. So I'm just going to put that right there. That is arbitrary. I don't know what that value is. I've just selected it. And I know I'm going up like that, and then the other side is going to look something like that. And we end up with something that looks like a parabola, and I know that because the derivative of a parabola is a straight line. With what I've got here, I actually could figure out the equation of this straight line, and from what we've understood about calculus, we could probably work backwards. If this is the derivative, we could probably figure out an equation for the antiderivative, and then using that value at 1, we could actually give a fairly precise graph of this. But I just wanted a sketch. Okay, here's another one. Now in this case, I'm giving you the graph of f of x, and I want a sketch of f prime of x. As I've been talking about throughout this lesson, where the slopes are equal to 0 are very important. So I'm going to first identify where slopes are equal to 0. And now this is interesting, because you have to ask yourself, is the slope equal to 0 along there? And what does that mean? Now, what does it mean? This is the graph of f of x, and I just want to reinforce that. What we're looking at here is y equals f of x. So we want to know the derivative. So the derivative of this would mean that at this point the derivative is equal to 0. That means I'm going to be passing through 0 there. At this point the derivative is 0. That means I'm going to be passing through 0 here. And strangely enough, and you'll understand why I think this is strange, at this point the derivative is 0, which means I'm going to be passing through 0 here. So those 3 points are on f prime of x. Now let's take a look at what we know about some intervals. For example, we know that, I'm going to switch the color of the line I'm using. So now that we've identified these 3 key points, because they are where the tangent is equal to 0, let's take a look at what's to the left of this one. So that's going to give me slopes that are, well, what can you tell me about that? The slope here is positive. So that means that f prime of x, so if I say that this slope is positive, that's another way of saying that f prime of x must be positive. So that means that over here my graph is positive. I don't know if the graph is positive like this. I don't know if the graph is positive like this. I don't know if the graph is positive like this. I just know that it's positive. I prefer, whenever possible, I'm going to try to draw a smooth graph. So I'm just, for now, I know it's positive, which means I know it's up here somewhere. And before I fill anything in there, I'm actually going to go to this side, and I'm going to take a look at the slopes I have along here. And I notice that, hey, those slopes are also positive, which means f prime of x is greater than 0. I have another positive slope here. And then over here, and you don't need to always be putting in these straight lines. It's probably a little bit of overkill by this point. Hopefully you're able to look at that and just say, oh, I can see f prime of x here. This is a negative slope. And then over here, f prime of x is positive. So what do we have going on here? F prime of x is positive. So now I know I'm positive up here. Here it's positive. Between here and here it's negative. And then over here it's positive again. So I need to draw a graph that touches these zeros, or passes through these zeros, that also passes through all of these bubbles. And so the graph that I have in mind to do that is going to look like this. Oop, that didn't do a very good job of that. And so if we now, I'm going to select those bubbles that I put in just kind of as placeholders, get rid of those. And I think I'm even going to get rid of those green lines. And now we take a look. Here the slope is positive because f prime of x is greater than 0. Here the slope is positive. It passed through 0, but it stayed positive. Now here it's high and positive, and here it's low and positive, but it's still positive. Then it passes through 0, goes to this side. It's now negative, which is reflected by this slope being negative, and then it's back to positive again. The hardest part you're going to have with this is going to be as you switch. Are you being asked to use f of x to sketch f prime of x, or are you being asked to use f prime of x to graph f of x? And of course, the order that you're being asked to do that absolutely matters, and you have to be really careful and make sure you are very clear about which one you're looking at and what's the relevance of each. Sorry, that 0 was bothering me. Okay, so I believe that's it for this lesson. That is it. So you've got some work here. Notice that in the homework I do specify I want you to do question number 4. I want you to do those algebraically. Okay, so keep that in mind. That means you're going to be taking derivatives, you're going to be using an interval table, factoring, that sort of thing.